Alright, for this lesson, we're going to start to take a look at the relationships between the volume of gases. Specifically, we're looking at Avogadros' law and how it pertains to gases undergoing chemical reactions and how we can connect the mole to volume of a gas. When Avogadro was doing his research, he was experimenting with hydrogen and oxygen gas, and he noticed that whenever he did an experiment with hydrogen gas, say he took 100 milliliters of hydrogen gas and he reacted it, it would react completely with 50 milliliters of oxygen gas, and it would produce 100 milliliters of water vapor. Say he did 50 mils of hydrogen gas, it would require 25 mils of oxygen and produce 50 mils of water vapor. And he found that there was a set ratio of 2 to 1 to 2 in this chemical reaction in terms of liters or units of gas. And during this time, a lot of scientists were experimenting. They were comparing mass relationships, and they couldn't quite figure out what Avogadro found here. And even with experiments such as with ammonia, when experiments with ammonia, decomposition of ammonia was done, you could take 8 milliliters of ammonia gas and you would decompose it with some heat and you get 12 milliliters of hydrogen gas and 4 milliliters of nitrogen gas. And again, these were fixed ratios. So Avogadro came to the conclusion that there must be something that connects the volume of gases to the number of particles in those gases. And so he came up with this idea that equal volumes of gases equal volumes of gases contain the same number of particles regardless of the mass. And so the volume of a gas is directly proportional to the number of molecules, and what that translates into is number of moles. So number of molecules, number of moles of gas. However, a big caveat to that is that the pressure and temperature are constant. And so in order to have this, we need to have standard conditions. Now, where does the mole fit exactly into this? Well, it turns out that the volume of 1 mole of any gas should be the same as the volume of mole of any other gas, according to Avogadro, if the temperature and pressure are the same. We have a standard condition. Thus, we can calculate what we call the molar volume of a gas. It's the volume of 1 mole of a gas, and it's expressed in liters per mole. So we see the small v here, that would be the molar volume. Now, in order to determine the volume of 1 mole of all gases, we need to identify this set of conditions. And this brings us back to our standard temperature and pressure, which was the first condition set out by chemists. That's where we have our pressure of 101.325 kilopascals, our temperature of 0 degrees Celsius, and it turns out that under these conditions, if I have 22.4 liters of any ideal gas, could be hydrogen, could be helium, could be methane, butane, any gas, if I have 22.4 liters of that, I have exactly 1 mole of that gas. Now, to do experiments at that temperature is very cold, so chemists also developed standard ambient temperature and pressure. And under these conditions, we have a little bit less pressure, 100 kilopascals. Temperature is a very nice 25 degrees Celsius. And our molar volume would be 24.8 liters per mole. So if I have just under 25 liters of a gas, that would be 1 mole of that type of gas. So depending on what standard conditions we're using, we can determine, if we know the number of liters of the volume of any gas, we can determine the number of moles of that gas. And this is going to become important later on when we start looking at ideal gas law and Dalton's law of partial pressures. So what we're going to do right now is jump to some problems. Look at a couple problems here. The first one, at STP, 1 mole of oxygen has a volume of 22.4 liters. So my volume is 22.4 liters, and my number of moles is 1 mole. Determine the mass and number of particles at 44.8 liter sample of the gas. So I know my other volume is 44.8 liters, and we know that the molar mass of oxygen, in order to do this question, because we need to determine moles, would be 2, because there's 2 atoms of oxygen in that diatomic molecule, 2 times 16.00 grams per mole, which is 32 grams per mole. What we need to find here is the mass and number of molecules of the oxygen gas. So we need to find N first, and then once we find N, our second thing to do is to find mass. So the solution, initially what we need to do is determine what the mass is. So we can set up a simple little ratio here. Because I want to find N, I'm going to put it on top. So I know that N1 over V1 is going to be equal to N2 over V2. Because there's a direct relationship between my moles and my volume, I have to put one over the other. Alright, if I don't, if I put them beside each other, that would be setting up an indirect relationship. And I know that I want to solve for moles, so it's easier to put it on top. So I want to get my moles, my second set of moles. So what I'm going to do is just cross multiply my V2 up. So I'm going to get N2 is equal to N1 times V2 over V1. So now I can solve for my final moles. So I sub in what I have. N1 is 1.0 mole times my V2 is 44.8 liters, all divided by 22.4 liters. Now, big thing here is to cancel out my units, and I'm going to be left with moles, looking pretty good. And so in the end, I get 2.0 moles of oxygen. So to find the mass of O2, it's going to be my number of moles times my molar mass. And this is back to our unit on stoichiometry. So I've got 2 moles times 32 grams per mole, and that gives me 64 grams. So 64 grams of oxygen gas would be the mass of the 44.8 liter sample. Now we can take a look at doing another example of this where we calculate the molar volume of nitrogen. So we have an empty steel container. It has a volume of 0.652 liters and a mass of 2.5 grams. We fill this container with nitrogen gas. The container has a mass now of 3.23 grams. The pressure of the nitrogen in the container is 97.5 kilopascals when the temperature is 21 degrees Celsius. Calculate the molar volume of nitrogen gas at STP. So, let's write out first what we are given. We know initially that our gas is 21 degrees Celsius. which, when we convert it to Kelvin, we add our 273, will give us 294.15 Kelvin. For these questions, I'm going to include the 1.5. For other ones, don't need to. It's pretty small decimal, but for this case, I'm going to include it. My pressure of my gas is 97.5 kPa. And my volume is 0.62 liters. Remember, that is the volume of the container. Sorry, 0.652. Now, I know the mass of my container is 2.5 grams, and the mass of the container plus the nitrogen gas is 3.23 grams. And I also know my conditions, STP, and I can determine the molar mass of nitrogen gas. Remember, nitrogen gas is N2 when you do that. So our temperature at STP is 0 degrees Celsius, which is 273.15 Kelvin. And pressure is 101.325 kilopascals. And the molar mass of nitrogen, because nitrogen molecule, there's 2 atoms, so we have to multiply 2 times 14.01 grams per mole, and that's going to give us 28.02 grams per mole. Okay, so first of all, we need to determine the mass of nitrogen. So to determine that, we need to take the mass of the container minus the mass of the container empty. So the mass of the container with nitrogen was 3.23 grams. That's the container plus the nitrogen. And we need to subtract the mass of the container without, so 2.5 grams. And we're going to get the mass of the nitrogen is 0.73 grams. Now we can determine the number of moles of nitrogen. And we know that moles is going to be mass divided by molar mass. In this case, it's 0.73 grams divided by 28.02 grams per mole. And we're going to get 2.605 times 10 to the minus 2 moles. Okay, so now we know how many moles we're dealing with. What we need to determine next is to determine the volume of gas that we're dealing with. Remember, in the end, we want to determine the molar volume. And molar volume, I'll just sketch this up here, is V equals volume of my gas over number of moles, right? And so we've now got number of moles. We now need to get molar volume. So how do we determine molar volume? Well, remember, we went from one situation where we had the mass, where we had the gas in one situation, and then we transferred it to another. So this is a combined gas law question. P1 V1 over T1 is equal to P2 V2 over T2. Alright, so we know what the gas is like inside the container, but what would the molar volume be if it was at STP, regular standard temperature and pressure. So we need to solve for V2 here. We're just going to highlight V2. Make it a nice color. There we go. V2. We want to get V2 on its own. So what are we going to have to do? Well, we're going to have to do whatever's on the bottom, we got to cross multiply up to the top. Whatever is on the top, we have to cross divide it down to the bottom. So V2 is going to be P1 V1 times T2, bring the T2 up, divided by T1 times P2. So now we get to sub all of our values in. So our initial pressure is 97.5 kPa. Our initial volume is 0.652 liters. And our final temperature is 273.15 Kelvin. Divide all that by our initial temperature, which is 294.15 Kelvin, times our final pressure, which is 101.325 kPa. And when we calculate that out, we get 0.583 liters. So now what we can do is we can determine our molar volume. And we take our volume, which is 0.583 liters, and we divide it by the number of moles, which was 2.605 times 10 to the minus 2 moles, and we get 22.4 per mole, which is what we should get at standard temperature and pressure. So by doing this, we just proved Avogadros' law that 22.4 liters is equal to 1 mole of gas, in this case of nitrogen. The next set of lessons will deal with the ideal gas law and Dalton's law of partial pressures.